Hello everyone, my name is Alena Rybakina and I would like to speak about PostgreSQL Optimizer Flaws and how we solved problems with them. Some information about me. I'm a core developer and I have been working in Postgres professional since 2021 and I have several patches were committed in PostgreSQL database or to any transformation, values to any transformations, and I have participated in extensions like QO and replanning, and I'll tell you about them in my talk. So, first of all, we are going to discuss how the optimizer works. We will discuss the cardinality estimation problems. I'll tell you about how the several solutions that we implemented to fix them, and we make a conclusion. So, how the optimizer works? First and foremost, we need to discuss the problem statement of the optimizer. And first and foremost, the optimizer needs to find the best plan command all possible. Unfortunately, the number of possible query plans grows significantly with the number of tables because we need to consider combinations, all of them. And the optimizer uses the dynamic programming algorithm to find the best query plan among others. And unfortunately, it guarantees that the query plan will be found, but might be non-optimal one. So let's consider it deeply. First and foremost, the optimizer chooses the query plan based on the costs of them, and it prefers it chooses the cheapest one. What do I mean? I mean that the optimizer prefers choose the query plan with the cheapest cost. And to estimate the cost of query plan, we need to estimate costs of their components and summarize them. And to determine the cost of one component of query plan, we need to estimate cardinality, selectivity. What is cardinality? Cardinality is the number of tuples produced after executing an operation. Let's consider an example. We have two tables, table 1, table 2, and so the result of Cartesian product between two tables will be equal to 9 because we need to match every row from one table with another. And what is selectivity? Selectivity is the fraction of rows from the Cartesian products of two sets that remains after the join condition is applied. Let's consider an example. We need only to know how many tuples will be matched to each other. So there are 3 tuples with 12 because it was repeated twice in table 1, and 11. So the number of tuples from this join will be equal to 3. Cartesian products was equal to 9. So the result will be 1/3. Because we need to divide 3 on 9, and but we can't use this schema in PostgreSQL database because we don't know cardinalities. But at the same time, we can estimate we can estimate selectivity, and based on the selectivity, predict the cardinality. So, PostgreSQL prefers using statistics. There are three kinds of statistics in the PostgreSQL database. One of them is non-common values. It is used when the number of distinct values is not so large. And histograms, in contrary, used when the number of distinct values is large. And the last statistics is represents the proportion of missing null values. So let's consider an example. We have a table that contains information about startups. So there are three columns. One of them is the name of startup company. The second one is country, where is startup is located, and the last one is values of startup. So we prefer, the optimizer prefers storing information about countries using MCV, most common values, because there are less number of countries in the world compared to the number of startups in the world. So startups will be stored in histogram. And let's consider how it works. So we need to estimate the cardinality for this query when the valuation of startups is less than 50. First and foremost, we need to determine the selectivity of MCV. It is the sum of frequencies before 50. And the next step is the determination existing columns, and we used statistical information about it. The next step is the estimation of selectivity from histogram. And this formula contains information like we need to find the relative position of bond in the histogram in a normalized range, and we need to determine spacing between histogram bonds in the remaining distinct values, and we need to estimate we need to estimate that our data distribution is not uniform, and so we use this selectivity information to determine total selectivity for this query, and it is equal 0.9. So the cardinality is equal to the multiplication between the total number of rows from table about startups and the total selectivity, and it will be equal to 207. So we have a problem here because first and foremost, the optimizer believes that optimizer believes that there is the data across the histogram bins distributed uniformly, and it might be wrong because sometimes we face the problems that one value can be repeated more often than another, and so it isn't a uniform distribution at all. And another problem is the optimizer used information about now elements only for particular column, but it doesn't store information how many now elements appeared after outer joins. So it leads to underestimation problem, and we will consider it on examples. And we have another problems here. Unfortunately, the optimizer believes that the data in columns are independent, and so it uses this formula by default. It can be solved with extended statistics, but we need to add information about it. So we know cardinality for this query. Let's consider how we can estimate the cost for example, for sequence scan. We know the cost for only one tuple, and it's like how expensive it will be for our system, for our CPU, to execute sequence scan algorithm only for one tuple, and we need to estimate for several ones, and it is the multiplication between the, for example, CPU tuple cost and number of tuples, cardinalities that we calculated before. And we need to we need to scan all pages from the table, and we need to estimate it too with multiplication between sequence page cost and pages. So the total cost for sequence scan for this for our query will be 170. So how the optimizer works? Let's consider our schema. When the user sends the query to the optimizer, parser splits it into tokens, and it checks that the grammar is correct. If the grammar is correct, if the grammar is correct, so the parser generates a parse statement and it sends it to analyzer. Analyzer checks that the user has access to the object that was mentioned in the query, and if it is okay, it sends it to tree rewriter. Tree rewriter can modify parse statement. And for example, it can add materialized view to simplify the process of generation of query plan for this query. And it generates a query tree, and it sends it to path generator. And our generation query plan begins. So first and foremost, path generator needs to estimate costs for components of query plan, and it needs to estimate cardinality for them, and after that it uses this information to estimate costs for the query plan. And it chooses the cheapest one, and it is optimal path, and it sends it into path plan generator. Plan generator generates query plan based on optimal path, and it sends it to the query executor. Query executor executes a query plan that was generated before, and the results will be sent to the user. Simple. What could possibly go wrong? If cardinality estimator estimates cardinality incorrectly, it leads to the fact that all system can be no, it isn't broken, but almost. Cost estimator estimates costs incorrectly for the whole plan. Path generator chooses a non-optimal path, and finally, query executor executes the query plan more longer than it was expected before. So let's consider the cardinality estimation problem here, because it is important, as we saw. If we have outdated statistics, or our data distribution is non-uniform, and if we have correlation between columns, or it's like other problems that present in our query plan, it leads to the underestimation problem or overestimation problem. But the main problem is the fact that the planner doesn't learn on its mistakes. So it repeats again and again to choose a non-optimal query plan, and it can't like to store their mistakes and use it to improve something. And our first project was to develop some tool that helps the optimizer to learn from its mistakes. And it was adaptive query optimization, AQO. It is a memory for planner. AQO, as I mentioned before, it is an extension, and this extension can store the actual selectivity of relations and for components of the query plan, and it shares this information with the optimizer, and it will be very helpful for the optimizer to generate more optimal query plan. And let's consider how it works. The main component of AQO is AQO data. As I mentioned before, it stores selectivity for some relations. What is relations and what is not? Nodes. Relations, it's one relation can represent a real table, view, or subquery that was mentioned in the from clause. Or it may be a joint relation between two tables, for example. Or it may be aggregate operation. It is like separate relation in the optimizer, and other relations present in the optimizer of PostgreSQL Optimizer. And what is plan? What is plan node? Plan node represents the physical operation used to access and process relations. So for base relation, it is sequence scan, index bitmap scan. For join relation, nested loop, hash join, merge join. For aggregation, it is group by operation, hash aggregate. So if you used explain analyze, for example, you might face this kind of algorithms that was used for the execution of query plan. So I think we understood this part. Let's go further. So how AQO works? How does AQO work? And we see the schema of the optimizers that we discussed before. And the first operation, it is not component, but operation of AQO is learning. So when query executor finishes executing the query plan, AQO gathers information from nodes of components of query plan. It is actual cardinalities, features. It's like the description of nodes. And it can update this information in AQO data based on the error of cardinality. Error cardinality is the difference between actual cardinality and predicted one. And it can improve it based on the error of cardinality. And when the optimizer begins, when the optimizer tries to generate a query plan for this query, it will use actual cardinality data from AQO, and it might be helpful for it to improve query plan. So let's consider the first problems that we faced and how we can fix it with AQO. We have two tables, table small, table large. Table large contains 1 million tuples, table small 100 tuples. We have left join between two tables, but we are interested in getting results on matched tuples. So, as an optimizer believes that the answer will be 1 one cardinality. But the real number of cardinality is 1 million, no, almost 1 million, because only 100 tuples are matched to each other in table large and table small. Unfortunately, no. AQO can fix this problem because it remembers actual cardinality and it shares this information with the optimizer. Unfortunately, this problem can't be solved with extended statistics and there are no possible tools to fix it with a PostgreSQL Optimizer for now. And as I mentioned before, the optimizer doesn't contain information about how many now elements contain how many elements can contain outer join. It only examines the now elements of column B from small table. And so, but it is this thread. It is like this example was considered in PostgreSQL hackers, and it is opening now because there are no solution for now. And so you can find more information about this, or maybe participate in it, and so it will be interesting. But our customers faced another problems. They are related to PostgreSQL. They are related to the wrong prediction of cardinality. So this part of query was generated. Okay. I'm a developer, and unfortunately, I have a lot of cases that was caused by 1C system. 1C system uses auto-generated system. No, it's like queries that was written by machine, and it might be like echoes. So this part of query, it's like it contains 200 lines of SQL query. It was generated by machine, and unfortunately, the optimizer could execute this query. It's like 1 hour. It was so long. Let's consider what was wrong with this query. Unfortunately, the planner can't use information from statistics and predict cardinality correctly if there was used aggregation function. So you can notice that after group aggregate, suddenly there was predicted 1 rows, but the real answer is almost 18,000. And it leads to the problem that several nested loops were chosen by the planner, and every nested loop tried to execute 18,000 tuples. So it leads to the fact that the query was executing for 1 hour. But we can solve this problem with a QO. A QO stores information about actual cardinality. Again, it shares this information with the optimizer, and execution time cut down to 3 seconds about it. So you can find more information about a QO. I had a talk in PGConf Canada last year. And QO is open source project, so you can look at it, and it is available in our products. So let's consider further developments. Unfortunately, a QO has disadvantages. One of them is related to the fact that we don't know what queries should be stored, before it's like suddenly our query will be executed more longer than we expected before. And and we need to update our cardinalities in the EQL data every time when our table changes, and it might be expensive for us. So let's consider another solution, and it was replaning. Replaning, like EQL, it stores information about actual cardinalities of nodes that was used in query plan, and but it works when it needs. For example, let's consider how it works. We have two components of replaning. One of them is replan data, it's like EQL data, and another one is like alarm clock for the optimizer. So if actual execution time, for example, exceeds the statement timeouts that we said before, it means that our query plan can't be generated wrongly. And it means that we need to replan it, but we prefer using actual cardinality that stores in replan data, and finally, it can improve our query plan. So our alarm clock is located in query executor, and for example, actual execution time exceeds statement timeouts that we said before, for example, and we save information about actual cardinality and query statement in replan data. We need rollback, because it's like we are not ready to send results to the user because our query has not finished yet. And we begin sub-transaction and sends this information about query statement to the analyzer, and the generation of query plan will begin again. And but this time, cardinality estimator will use actual cardinality that was stored in the previous phase of query generation. So this solution showed impressive results on join order benchmark. So you can notice that that only with 10,000 milliseconds we got several queries were improved significantly, and there are no only few queries have had lower execution times that it was without replanning. And so let's consider these queries. For example, in my practice, queries 26C and 31C, they are complicated for the optimizer. And so you can notice that the execution time cut down to 52 seconds, and so it was fine. And statement timeout was set 1,000 milliseconds. And 31C, this query, the execution time cut down to 2 seconds, and so there are, it's like, yes, there are 2 attempts for the replanning, 2 attempts for the replanning used to produce more appropriate query plan. So let's before we go further, I'll tell you a funny story from my work experience. Oh, just relax. So there was a query again from 1C, and it contains 500 lines of query plan. And the executor tried to execute it for 3 weeks, and to be honest, we don't know actual execution time because we stopped it. So I was a June developer, and this query looks like this. It's like a kind of terrifying and comprehensible query from the word of 1C, and I had no idea what was wrong with it. I tried to use SQL. It's like the first solution that can be used in a simple way, but it did not work, and we had like withdraw version of replanning, and I tried to use it. And it showed impressive results because 3 weeks cut down to 4 milliseconds. But we needed, it's like statement timeout was set to 1 minute, and total execution time, it's like with the replanning process, took 6 minutes. So we called, hooray, yes, we did something. And so let's discuss what was wrong with this query. First and foremost, you can notice that nested loop, it's like a scanned sequence scan 35,000 times. And it's like it was the main issue why this query executed so long. But why nested loop was generated by the planner? It was caused underestimation problem again and again because of hash, because of aggregation function. So optimizer can't use statistical information because of group aggregation, because it caused the fact that our data distributed non-uniformly, and so we had a problem. Okay. So you can find more information about it in the article that Andrei Lepihov wrote in Substack, and unfortunately replanning is not open source, but it contains in Postgres Pro Enterprise, and Andrei Lepihov prepared a Docker container, so you can use it. But there are some disadvantages of replanning. One of them is related to the fact that it might be resource consuming for the system, because it's like it needs CPU cycles to replan it again and again. And when we developed replanning for the PostgreSQL, it needs a lot of core level code. So because it's like we needed to rewrite a receiver to avoid the situation when we are not ready to send results to the user, and we can fix problems like when the optimizer faced. When the planner predicted cardinality incorrectly, like underestimation problem. And so the next our solution is switch join. Choose hash join on time. Switch join is an extension of PostgreSQL again, and it saves 2 plans. One of them was generated by the optimizer based on the cardinality that was predicted before, and another one is hash join. We push the optimizer generate hash join, and we added an engine of switching from one algorithm to another, from nested loop to hash join. So how does it work? We execute initial query plan, and we consider actual cardinality of outer node of nested loop. And we need to preserve results via materialized node, because we don't want to recompute this node again, parent A on the picture. And we check the actual cardinality exceeds does actual cardinality exceed the row count limit or not? And if it is, we switch to hash join algorithm, and we need to only to rescan parent A, because we preserved results before via materialized node. So for the as for the implementation of switch join, we needed only to determine the row count threshold to decide when we need to switch from nested loop to hash join, estimate cost for switch join, because sometimes the optimizer should not use it, and added materialized node to avoid recomputation of observed node. It was relation A on the picture. And we need to add engine to switch from one algorithm to another. So we realized that with custom nodes. Custom nodes are user-defined planner or executor nodes, and so they can contain several subpaths or child nodes, and we needed to use only one planner hook, set real path list hook. So you can, and we checked it on TPCH benchmark. So you can find that 2 queries were improved significantly with switch join extension. Let's consider what was wrong with them. So as for 22 SQL, you can notice that there is a sub-plan here. Unfortunately, the planner does not predict doesn't predict cardinality for subplan before executing it, and to be honest, it isn't possible for the query plan, because it generates a query plan. It's like for the main part and for the subquery part, and so it can't be solved for now with PostgreSQL extended statistics or other methods. And so we see underestimation problem here, and it leads to the fact that the optimizer, because of underestimation problem, chose nested loop algorithm, and nested loop tried to execute 1 million rows, as I remember. As for switch join contains 2 algorithms, nested loop and hash join. It noticed that underestimation problem, there was underestimation problem here, and it chose hash join algorithm, and execution time, cut down to several minutes. From 30 minutes to several minutes, it's like 5 minutes, as I remember. It's like impressive. It was impressive. And another query, it was 9th query. So you can notice that the planner chose nested loop again because of underestimation. So nested loop tried to execute 5 million tuples. And it was caused the fact that these columns represents a single interconnected entity, and so it can be fixed with extended statistics. I'll show you later. And so with switch join, contains two query plans, one of them with nested loop, another one with hash join. And it noticed underestimation problem here, and it prefers using a hash join algorithm. Execution time cut down to several minutes again. As I mentioned before, when we define distinct values with extended statistics, so we got almost the same results. So you can find more information about switch join here. I talked about it in PGCon for Canada this year. And I prepared a Docker container for switch join because it is not open source again project. And so, as for conclusion, when we consider that in my practice, query plan can be generated wrongly by the optimizer because of underestimation problem. Because it's like I face a lot of queries that are related to this problem more often. And so sometimes we can't fix it with extended statistics or other tools, to be honest, and we can use only EQO or planning or switch join. It depends on like several factors. So if you have a question, I'll answer on them.